Hello everyone, I'm so glad that you're back. Today what we're going to do in AP Calculus is determine limits using our graphs, and we're also going to determine limits using numerical data. As we begin, make certain that you are focusing on using the correct notation throughout the entire lesson. So limits through graphs and numerical data. So my expectation is that you've completed the lesson preview to the best of your ability. So having done this, let's have a brief discussion. As you drew the function f of x equals square root of x, you are also asked to plot the point 4, 2 and draw the secant line through the values x equals 1, x equals 3, and x equals 5. So if you found the slope of each secant line, those values would be 0.333, 0.268, and 0.236. So using these results of our graph at f4,2, we want to figure out what the slope of the secant line is at 4,2. But to find the slope of the secant line at 4,2, maybe you used your two values that were given to estimate. So if you got some answer for the slope that was between 0.268 and 0.236, then you did a really great job. Now, what we really want, though, is to find the slope of the tangent line through 4,2. And you can see that if we tried to take f at 4 minus f at 4 over 2 minus 2, we get something ridiculous like 0 over 0, even though we know the answer for that slope needs to be somewhere between 0.268 and 0.236. So we're going to have to come up with some way to estimate the slope of the tangent line, and hopefully limits will be part of that conversation. So Zeno sets up actually 3 different paradoxes for us, and each one of them has a really interesting takeaway. As you read about Achilles and this tortoise, I hope that you agree, or maybe you don't, with Zeno's conclusion that Achilles will never actually catch this tortoise. His second paradox has to do with an arrow. So we're trying to shoot an arrow at a target. The arrow travels halfway there, and then halfway some more, and halfway again. And if we keep taking these finite halfway trips, we're never actually going to hit the target, because as you add each of those half durations, there's always more that need to be added, and you will never hit the target. So what Zeno does, and you can read about his third one, look that up on your own, is he sets up the idea of limits. The concept of limits in mathematics is really the basis of all calculus. So if we take limits and we approach a certain value for x, the path that we're traveling for x is going to follow the path of f of x. And f of x, of course, is that y value. So limits are trying to understand, as x is traveling, what does the path of f of x look like? So calculus is the study of rates of change and area under a curve. But for each one of the concepts that we study about rates of change, limits are going to be used to create our definitions. The limits are also used in areas under the curve. Limits, in general, are used to approximate values of functions. And well, let's look at the notation for a minute. If we think about the limit as x approaches a for f of x equals L, so that's how this is read, but f of x is some function. And these functions can be represented graphically, they could be represented through data tables, but they could also be represented through algebra. So all 3 of these representations need to be fluid within our minds so that we can go back and forth from graphs to datas to algebra. Now, as we look closer at our notation for limits, let's think about what this concept might mean. L, first of all, is just a number. So L is a number, and it's used to estimate the value of y. And the reason I say it's a value of y is because of that f of x. So f of x and y are often used interchangeable. And these are as x is approaching some sort of value of a. So as x is approaching, now let's look more closely at as x approaches a. So when I say this, this means from both sides of a. So from both sides, not the right side, not the left side, but both sides of a. So we want to be very clear that x is approaching from both sides. So let's jump right in. We have an absolute value function that we're going to explore first. But notice the absolute value function that I've chosen for you has a hole in the vertex. But not only does it have a hole in the vertex, there's some sort of weird point sitting up here, just like minding its own business. So with that in mind, let's take a look at this notation. I want the limit as x approaches 2 of f of x. Now, when I write the limit as x approaches 2 for f of x, that means I want to approach 2 from both the right and left-hand sides. Now, 2 is an x value, so I'm approaching 2 on the x-axis, but I want to look at the y values as I approach. So that means I need to look at the y values as I approach from the left side and the right side of my function. Now, the y value, I hope that you can see, is on the number 1. Now notice approaching is the word that I've been using. I'm not touching, I'm approaching. So if I'm approaching 2 from the right and left side, the y value is tending to go towards 1. Now, when I look at the limit as x approaches the number 5, so that's going to be something a little bit different. So instead of the 2, let's start approaching a 5. And let's see here, when we do that, we're coming from the left side and the right side. Now you might be asking yourself, how do I know I'm looking at the left and right side? And the answer to that is I haven't specified either side, therefore I must be approaching from both sides. So coming from the left and the right side, let's see here. The y value looks like it is 4 as we approach from the left and the right side. Notice though, once again, I'm not touching the number 5. I'm approaching the 5. Let's see what happens as I approach x is -1. Left side and right side. I draw my arrows on my function to help figure this out. Well, the y value looks like the answer is 4 for this. So that's approaching. Now, if we look at questions D, E, and F, that's in function notation. And as you recall, what it means is that we're going to let x equal 2 for question D. And the question is, when x is 2, what does y equal? When you look at your function, when x is 2, let's see here, that y value is going to be the number 3. So f at 2 is going to be equal to 3. Notice the limit as we are approaching is different than the answer when we are actually touching. F at 0, when you look at the graph, is going to be 1, 2, 3. So I'm touching the value 3 when x is 0. And when x is -1, let's get rid of some of this again. When x is -1, let's see what happens as I touch -1. Aha, the y value is 4. So consider the difference between question C and F. The limit is approaching, but it doesn't actually touch the 4. I can't say that enough. But f at -1 does equal the value of 4. All right. Now, as we look at our next question, things change on us again. Change is good. That's why we're studying calculus, right? All right, I have a piecewise function, and this piecewise function has slightly different notation happening. Question A says I'm approaching 1, but notice it has that little minus sign next to it. That little minus sign means that I am approaching 1 from the left side. So if I'm approaching from the left side of 1, let's see, right, left side of 1, then it looks like my answer should be 2.5. Okay, now, if the superscript with a minus sign means left side, then the superscript with the plus side must mean I'm looking at the right side. So from the right side, let's see here, it looks like from the right I have 1.5. Now, the next notation. If you see x is going towards negative infinity, that means that we're looking at the left tail of your graph. So the left side of my graph, let's see, my tail, this is the left tail. It looks to me like my y values tend to go towards negative infinity. And then if I look at the right tail for x goes to positive infinity, that to me looks like it's flattening out at 1.5. So I have a horizontal asymptote there. Now for g at 1, okay, I'm touching again. I'm going to touch the value for g equals 1. And when I touch g equals 1, that's going to be the closed circle on this graph at 1. So that means g at 1 is 2.5. So f at -5. All right, so I kind of covered up where -5 is. Let's go over here on the left side of my graph and take a look. If I do that, it looks to me like -5 gives me a -1/2 as my value. All right, so one other thing I want to point out from this piecewise graph. Notice I didn't ask you for the limit as x approaches 1. Recall from what we did earlier, I have to put the f of x or it's wrong. If I'm approaching 1, that means I need to approach from the left side and the right side. And if that happens, do you see how they go to two different answers? The left side doesn't equal the right side. So if your left doesn't equal the right, there's actually no limit. The limit does not exist as x approaches 1. And that's a big deal. So let's take that idea and move forward to our next example. For example 3, you can see that we have some vertical asymptotes that we want to explore. So let's look at 2 from the left side. So here's 1 and then 2. So if we're approaching 2 from the left side, not touching, recall we are not touching. So we take our idea, we're going to climb up 2. Notice what's happening here. The graph is going upwards and upwards. So the 2 from the left-hand side is positive infinity. We represent that graph as going upward as positive infinity. Now we're going to approach 2 from the right-hand side. So from the right-hand side of 2, let's see what our graph will do this time. So we're going to take our graph, we're going upward, and look at that. The graph is going towards positive infinity again. Now, if we're thinking about x approaching 2, which means from both the right and the left side, that's going to show us that the x values are both heading upward to positive infinity. So along this particular vertical asymptote, both graphs go to positive infinity. Now, h of 2, talks about touching the graph at 2. And you can see that there are no values on the line x equals 2. So h of 2 does not exist on this graph. All right, now let's see if you remember. When we have a left-hand tail, that means we're going to follow the tail to the left side. Once again, look at that. It looks like a horizontal asymptote. It's flattening out. It's flattening out to the y value is 0. So the left tail is going towards 0. The right tail, let's follow the right-hand side of the graph and see what it's doing. This one is also flattening out to 0. So for the vertical asymptotes, it is possible to have both of them heading upward. They could go in different directions, but we do want to make certain we understand that the limit as x goes to 2 in this particular example does exist. And now for our oscillating function, you knew this was coming. For an oscillating function, in this particular case, it looks like a cosine function, but that's irrelevant. I want to look for x approaching 0 from the left side. So approach from the left side, and I can see that my y value is heading towards 1. Now approaching 0. Ooh, so that means I have to approach from both sides. This time, I didn't give you a separate question, but both sides do seem to be pointing to the same y value, and that would be 1 as well. Now, think about your left tail for a minute. Here's my left tail. It looks like it's going downward, but I want to take into consideration what's happening with the rest of the graph. Even though we can't see it, a pattern has been established. It should start heading back upward. This tail is not going towards some number L. It's going to keep going up and down, up and down. And since it doesn't go to one value for a number, this is an oscillating function. The tail end behavior does not have a limit that exists. On the right-hand tail, look at this, the same thing's happening. The pattern's been established that it's going to go back up. So this tail end behavior does also not exist. So this is an oscillating function. This happens a lot with your trig functions, and you had to keep an eye on the tail end behavior because sometimes they just don't have limits. So I want to revisit piecewise functions for a minute. So let's consider a function that has a horizontal piece, an open circle at 1, then maybe it jumps up and doesn't actually touch. So if I'm looking at this piecewise function, the limit as x approaches 1 for my function f of x. So as I'm approaching 1, you can say from the left-hand side that it is approaching, I don't know, how about this is y is 1, but on the right-hand side, it's approaching a different value. And if they're approaching different values, then the answer would be does not exist. So you have to make certain that the left side and the right side are approaching the same y value in order for the limit to exist. So from our previous work, we can see that there's definitely going to be some sort of limit existence idea. If we take the limit as x approaches a from the left of our function, and that equals the limit as x approaches a from the right of our function. And then they're both said to equal L. If this is true, then the limit does exist. But so our limit will exist if and only if the right side is equal to the left side is equal to some number L. Now, as we were looking through our examples, there were several loopholes that we needed to think about. So for example, the limit as x approaches negative infinity for a function is going to exist only if it goes to positive or negative infinity or some number L. And for the limit as x approaches 2 from the right to exist, that needs to also go to some number L. Finer points that we want to consider here. So the answers to all of your limits, those are y values. The limit as x approaches positive infinity is describing what's happening to the right tail. Negative infinity talks about your left tail. If your limit is going to positive infinity, then the function goes up. If the limit goes to negative infinity, then your function goes down. If your limit goes to two different values, that's a bad thing, then the limit does not exist. If your limit goes to both positive and negative infinity, then the limit does not exist. If your function oscillates as your x is approaching some value, then your limit does not exist. So, limit existence. Limit from the left must equal the limit from the right, must equal some number L, or even possibly positive or negative infinity. All right, so you've come to some lesson practice. It's time to think about the different ideas that we've been talking about. These come from your book, and I want you to practice this group of problems, but only for 10 minutes. So set a timer, hit pause, and work for 10 minutes before you move on to the next slide. So for the last part of our lesson, we are going to make a table of values to look at our numerical limits. So get your calculators out because you need to practice making tables of values. The only way that you're going to be able to get this is through the practice. So get those calculators out so that I can discuss how to use it with you. So we're going to start by looking at the limit as x approaches 1 for x to the third minus 1 all over x minus 1. When you use your calculator, I want you to type in under y1. I want that to be equal to. Use parentheses to separate your numerator from your denominator. So type in parenthesis x to the third minus 1, close your parenthesis, divided by parentheses x minus 1. The common mistake that people make is that they forget to put this parenthesis around their denominators and their numerators. All right, now we're going to make a table of values using your calculator. So if you have a TI-84 to make your table, we're going to go to second table set. I want you to set the independent variable as ask because we want to actually type in the values as we approach 1. So once you've set it for ask, go to second table and we're going to fill in all the x values. Now y1 should be in column 2. If you do not see y1 in column 2, then you're going to have to get a hold of me and I will help you figure it out or look it up on the internet how to use the calculator for tables. All right, so let's assume all is well. And you have your y1 in column 2. Now notice, we were approaching 1. So to approach 1, we want to come from the left-hand side. And these are numbers, 0.9, 0.99, 0.999, that are getting really close to 1 from the left-hand side. So put those numbers into your left-hand column. Now, on the right side, notice we have 1.1 and then it's going to 1.01 and we're getting really close with 1.001. And we're trying to get to 1, but we're not allowed to actually touch the 1. So don't fill 1 in unless you want some sort of error into your calculator. You should have all the values now in your column since you set the calculator to ask. Notice your x values are getting very close to 1 from both sides. Now let's interpret what your calculator is doing. First of all, order of operations always matter. The parentheses around your numerator and denominator always matter. When you interpret your values, if the values do not converge, the limit may not exist. If the values are very large, the limit may be going to infinity. So keep an eye on that because maybe 20,000 doesn't seem like infinity to you, but it might be infinity if you get a little bit closer. If your values are written in scientific notation, so if, for example, you see your calculator says 3 times 10 to say the negative 15, interpret that as 0 and write the number 0. Please don't write 0.000000. Just write it as equals 0. All right. So using a calculator, make certain that you have entered the information correctly and then interpreted your information. So as you see, the limit as x approaches 1 for this problem is actually equal to 3. So if you got 3 as your answer, you are correct. So for the rest of the lesson practice, you have been given tables of values for numbers 5 and 6 to use. Then you're going to make your own tables of values for numbers 7, 8, 9, and 10. Now, number 9, look, it has an absolute value function you will find that in your calculator under Math and then ABS. So look under your Math, ABS, in order to find the absolute value function. Your lesson follow-up for today, you're going to be working on the odds, numbers 1 through 25 on page 55 and 56. Now, just so that you know, when you are working for anything related to AP, 3 decimal places is the AP standard. So everything you do has to be correct to the 3